On Wednesday, June 25th, there were 18,135 cases in Dallas, Texas of COVID 19. Dallas has a total population of about 1,345,000. We have to assume that at the start of the clock, the cases are growing at approximately 3% per day. Can we create a logistic model for the predicted future growth of the cases? So, I'll draw a graph of cases versus time. So, there was really only about a small fraction of the people infected at the start, 18,000 versus a million. So, it's really just small starting value. So that's going to be called y of 0. If we do L over 1 plus A, we should be finding A by plugging in the initial cases of 18,135. That goes here. And then you want to use the 1,345,000 as the upper limit. And then we should be able to solve for A. Then from there, the cases are going to grow logistically to make a graph, something like that. Okay, so I'll do that algebra down here. You want y of 0 equals L over 1 plus A. You gotta do 18,135 equals 1,345,000 over 1 plus A. Okay, then we would multiply this 1 plus A to the other side. This makes it cancel over here and reappear over here. Okay, now we'll divide by the 18,000. Like it's 74.16598. Then we'll subtract 1. So A is 73.16598. Now they want the value of K. So when we're plugging in for K, we have to use this formula. P times 1 plus A over A. So P is the percent growth at the start of the clock. And they had said that the cases were growing at 3% per year. So I'll use 0.03 for P. And now that I just solved for A being 73.16, I'll plug that in here. But it's got to go in here as well as down here. So K is 0.03. 1 plus 73.16598 over 73.16598. Alright, so I'm getting K is 0.03041. So at that point, we should be able to construct the equation. So we put our upper limit as the 1 million. A was 73.166. And then for the K, we put in 0.0304. When you actually construct the model, you may want to include more digits than that. That's rounded. But now that we have that, it says, according to the model we created, how many days would it be until 60% of the Dallas population has been infected? So just for a quick answer to this, like the fastest answer we could get could be found through technology. So just do y of t equals 1,345,000 over 1 plus 73.1659 e to the power of negative 0.030410027 times t. So this should create the logistic function that models these cases. We want to see it level off at 1,000,000. Yeah, 1,300,000 cases there. We don't need to see that far in time. Yeah, that's better. So if you were to take the total cases, the 1,345,000, like the upper limit, if you take the upper limit and multiply it by 0.6, this is the number of cases that the problem's asking about, 807,000 cases. Like if we just type y equals 807,000, then we could see the level of cases that they're looking for. So they're looking for, it would be 154.5 days, apparently. I mean, that's a quick way to find the answer, but it is good to know, like, the algebra way of finding that. So, to do it through algebra, you want to start with the original formula of 1,345,000. You start with your mathematical model. And that represents your cases. So just now set that equal to 60% of the upper limit. So what'll end up happening is these are on opposite sides, so they cancel. And now you just have to solve the equation of 0.6 equals 1 over 1 plus 73.16598 e to the negative 0.0304t. The way to solve that would be to multiply this entire denominator to the other side. So you'd get 0.60, 1 plus 73.16598 e to the negative 0.0304t, and then set that equal to 1. Then you would now divide by the 0.60. Oops. Okay, so then you get about 1.66 repeating. Okay, then the parentheses are alone on a side, so they could go away. You'd now subtract 1. Divide by 73. I get 0.009. Then we'd have to take a natural log of both sides. So that would bring this down. Then we divide. $154.5 days.